when installing a 75 kV ampere dry-type transformer to supply a lighting and branch circuit panel board. Understanding the National Electrical Code, or NEC, requirements for conductor sizing is crucial. Let's examine the primary and secondary conductor sizing, as well as the equipment grounding conductor, or EG, requirements based on the NEC. Firstly, for primary conductor sizing, NEC Table 310.16 dictates that the minimum ampacity of the primary conductors must be at least 125% of the transformer's primary current rating. Given a transformer with a 480 volts primary and a 90 amps primary current rating, the calculation is 90 amps multiplied by 1.25, which equals 112.5 amps. The question mentioned using number 2 XHHW or THHN copper conductors. According to NEC Table 310.16, these conductors, when rated at 75 degrees Celsius, have an ampacity of 95 amps. Since 95 amps is less than the required 112.5 amps, number 2 conductors are not suitable for the primary feed. Secondly, let's look at secondary conductor sizing. NEC Table 310.15 B16 specifies that the minimum ampacity of the secondary conductors must be at least 100% of the transformer's secondary current rating. For a 120/208 volt secondary with a 208 amp secondary current rating, the calculation is 208 amps multiplied by 1, equaling 208 amps. The original question mentioned using 300 cm XHHW or THHN copper conductors. These conductors, rated at 75 degrees Celsius, have an ampacity of 225 amps. Since 225 amps exceeds the required 208 amps, the 300 cm conductors are acceptable for the secondary feed. Thirdly, concerning equipment grounding conductor sizing, NEC Table 250.122 governs the sizing of the equipment grounding conductor. It states that the equipment grounding conductor must have an ampacity equal to at least 1/4 of the ampacity of the largest phase conductor. In both the primary and secondary circuits, the largest phase conductor is the one with the highest ampacity. For the primary side, using number 2 XHHW or THHN copper conductors, although not permissible due to ampacity requirements, would have a rated ampacity of 95 amps at 75 degrees Celsius. Therefore, the equipment grounding conductor must have an ampacity of at least 95 amps divided by 4, which equals 23.75 amps. For the secondary side, the 300 cm XHHW or THHN copper conductors have an ampacity of 225 amps. Therefore, the equipment grounding conductor must have an ampacity of at least 225 amps divided by 4, which equals 56.25 amps. Number 8 copper conductors have an ampacity of 39 amps at 75 degrees Celsius, while number 6 copper conductors have an ampacity of 85 amps at 75 degrees Celsius. Consequently, number 8 copper is suitable for the primary equipment grounding conductor, and number 6 copper is suitable for the secondary equipment grounding conductor. In summary, to correctly size transformer conductors, firstly calculate the minimum ampacity required for the primary conductors, ensuring it meets at least 125% of the transformer's primary current rating, consulting NEC Table 310.16 for appropriate conductor types and ampacities. Secondly, determine the minimum ampacity required for the secondary conductors, ensuring it meets at least 100% of the transformer's secondary current rating, referencing NEC Table 310.15. B16 for conductor selection. Thirdly, calculate the minimum ampacity required for the equipment grounding conductors, ensuring they meet at least 1/4 of the ampacity of the largest phase conductor in both the primary and secondary circuits, consulting NEC Table 250.122 for proper sizing. Based on these calculations, number 2 XHHW or THHN copper conductors are insufficient for the primary feed. A conductor with a higher ampacity is required. The 300 cm XHHW or THHN copper conductors are suitable for the secondary feed. Number 8 copper is suitable for the primary equipment grounding conductor, and number 6 copper is suitable for the secondary equipment grounding conductor. Always consult the most recent edition of the NEC and local electrical codes for the most accurate and up-to-date requirements. Also, remember to account for ambient temperature correction factors and conductor dirting factors as specified in the NEC, especially when conductors are installed in raceways or conduits with multiple conductors. These factors can significantly impact the allowable ampacity of conductors. To elaborate on ampacity correction and dirting, firstly, temperature correction is necessary when conductors are installed in environments with ambient temperatures exceeding 30 degrees Celsius or 86 degrees Fahrenheit. The NEC provides correction factors in Table 310.15 B2a, which must be applied to the conductor's ampacity rating. These factors reduce the allowable ampacity to prevent overheating and insulation damage. For example, if a conductor with a 75 degrees Celsius insulation rating is installed in an environment with an ambient temperature of 40 degrees Celsius, the correction factor might be 0.91. This means the conductor's ampacity must be multiplied by 0.91, reducing its allowable current carrying capacity. Secondly, conductor dirting is required when multiple current carrying conductors are installed in the same raceway, cable, or enclosure. The NEC specifies dirting factors in Table 310.15 B3a, which reduce the allowable ampacity based on the number of conductors. The purpose of dirting is to prevent excessive heat buildup due to the proximity of multiple current carrying conductors. For instance, if there are 4 to 6 current carrying conductors in a raceway, the allowable ampacity of each conductor must be reduced to 80% of its original rating. If there are 7 to 9 conductors, the ampacity must be reduced to 70%. These dirting factors are cumulative with temperature correction factors. This means that if both temperature correction and conductor dirting apply, both factors must be applied to the conductor's ampacity. Consider a scenario where number 2 XHHW copper conductors are installed in a raceway with 5 other current carrying conductors in an ambient temperature of 40 degrees Celsius. The conductor has an initial ampacity of 95 amps at 75 degrees Celsius. The temperature correction factor at 40 degrees Celsius is 0.91, and the dirting factor for 6 conductors is 0.8. Firstly, apply the temperature correction factor. 95 amps multiplied by 0.91 equals 86.45 amps. Secondly, apply the dirting factor. 86.45 amps multiplied by 0.8 equals 69.16 amps. Therefore, the allowable ampacity of the number 2 XHHW conductor in this scenario is reduced to 69.16 amps. This example underscores the importance of considering both temperature correction and conductor dirting when sizing conductors, especially in environments with high ambient temperatures or when multiple conductors are installed in close proximity. Furthermore, it's crucial to consider voltage drop when sizing conductors, particularly for long circuit runs. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Excessive voltage drop can lead to inefficient equipment operation, reduced lighting output, and potential equipment damage. To calculate voltage drop, the following formula is used. Voltage drop equals 2 multiplied by the length of the conductor in feet multiplied by the current in amps multiplied by the impedance of the conductor per foot divided by 1000. The impedance of the conductor can be obtained from NEC Chapter 9, Table 8. If the calculated voltage drop exceeds the recommended limits, larger conductors must be used to reduce the resistance and impedance of the circuit. For example, consider a 208-volt circuit with a 100 amps load and a conductor length of 200 feet. Using number 2 copper conductors, the voltage drop calculation might reveal a voltage drop of 7%, exceeding the recommended 5% limit for feeders. In this case, upgrading to a larger conductor size, such as number 1/0 copper conductors, would reduce the voltage drop to an acceptable level. In addition to temperature correction, conductor dirting, and voltage drop considerations, it is also important to ensure that conductors are properly protected by overcurrent protection devices such as circuit breakers or fuses. The overcurrent protection device must be sized to protect the conductor against overload and short-circuit conditions. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes in Table 310.16. Generally, the overcurrent protection device should not exceed the ampacity of the conductor it protects. However, there are exceptions to this rule, such as when the conductor is part of a motor circuit or when specific equipment requires a higher overcurrent protection rating. For example, a number 12 copper conductor with an ampacity of 20 amps is typically protected by a 20 amp circuit breaker. However, if this conductor is part of a motor circuit, the overcurrent protection device might be sized higher to accommodate the motor's inrush current during startup. Always consult the NEC and equipment manufacturer's instructions to determine the appropriate overcurrent protection for specific applications. Another important aspect of conductor installation is ensuring proper termination and splicing techniques. Improper terminations and splices can create high resistance connections, leading to overheating, voltage drop, and potential fire hazards. The NEC specifies requirements for conductor terminations and splices in Section 110.14. These requirements include using listed and labeled connectors, ensuring proper torquing of connections, and providing adequate support for conductors. When terminating conductors on equipment terminals, it is important to use connectors that are specifically designed for the type of conductor being used. For example, aluminum conductors require the use of connectors that are rated for aluminum to prevent corrosion and galvanic action. When splicing conductors, it is important to use splicing methods that provide a secure and reliable connection. Common splicing methods include using mechanical connectors, such as split bolt connectors or set screw connectors, and using compression connectors, which are crimped onto the conductors using a specialized tool. All terminations and splices must be properly insulated to prevent electrical shock hazards. In addition to these general guidelines, there are specific requirements for conductor installations in certain locations, such as wet locations, hazardous locations, and healthcare facilities. The NEC contains detailed requirements for these types of installations in Chapters 5, 6, and 7. In wet locations, conductors must be listed for use in wet locations, and raceways and enclosures must be designed to prevent water from entering. In hazardous locations, conductors, raceways, and equipment must be designed to prevent ignition of flammable gases, vapors, or dust. In healthcare facilities, conductors and equipment must be designed to minimize the risk of electrical shock to patients and staff. Always consult the NEC and other applicable codes and standards to ensure that conductor installations meet the requirements for the specific location. To further clarify the NEC requirements, consider the following examples. Example 1. A 75 kV ampere transformer with a 480 volts primary and a 208 volts secondary is installed to supply a panel board. The primary current is 90 amps and the secondary current is 208 amps. The primary conductors are number 3 copper THHN conductors and the secondary conductors are 350 mcm copper THHN conductors. The equipment grounding conductors are number 8 copper for the primary and number 6 copper for the secondary. The ambient temperature is 35 degrees Celsius and there are no other conductors in the raceway. Are these conductor sizes compliant with the NEC? Firstly, check the primary conductor size. Number 3 copper THHN conductors have an ampacity of 100 amps at 75 degrees Celsius. However, since the ambient temperature is 35 degrees Celsius, a temperature correction factor must be applied. The correction factor for THHN conductors at 35 degrees Celsius is approximately 0.94. Therefore, the corrected ampacity of the number 3 copper conductors is 100 amps multiplied by 0.94, which equals 94 amps. Since the primary current is 90 amps, the number 3 copper conductors are adequately sized. Secondly, check the secondary conductor size. 350 MCM copper THHN conductors have an ampacity of 310 amps at 75 degrees Celsius. Since the secondary current is 208 amps, the 350 MCM copper conductors are adequately sized. Thirdly, check the equipment grounding conductor sizes. Number 8 copper has an ampacity of 40 amps, and number 6 copper has an ampacity of 55 amps. According to NEC Table 250.122, the equipment grounding conductor must be sized no smaller than what is shown in the table based on the overcurrent protective device. The number 8 copper is properly sized for the primary. The number 6 copper is properly sized for the secondary. Therefore, all conductor sizes are compliant with the NEC. Example: to a 100 amp circuit is installed to supply a motor. The conductors are number 3 copper THHN conductors, and the circuit is run in a conduit with 6 other current-carrying conductors. The ambient temperature is 40 degrees Celsius. What is the allowable ampacity of the conductors? Firstly, determine the initial ampacity of the number 3 copper THHN conductors. According to NEC Table 310.16, number 3 copper THHN conductors have an ampacity of 100 amps at 75 degrees Celsius. Secondly, apply the temperature correction factor. The correction factor for THHN conductors at 40 degrees Celsius is approximately 0.88. Therefore, the corrected ampacity is 100 amps multiplied by 0.88, which equals 88 amps. Thirdly, apply the dirting factor for 6 current-carrying conductors. According to NEC Table 310.15, the dirting factor for 6 conductors is 0.8. Therefore, the dirted ampacity is 88 amps multiplied by 0.8, which equals 70.4 amps. Therefore, the allowable ampacity of the number 3 copper THHN conductors in this scenario is 70.4 amps. Since the circuit is rated for 100 amps, the number 3 conductors are not adequately sized and must be upgraded to a larger size. Example 3: a 240 volt circuit is installed to supply a piece of equipment located 300 feet from the panel board. The equipment draws 40 amps. Number 8 copper conductors are used for the circuit. What is the voltage drop on the circuit? Firstly, determine the resistance of number 8 copper conductors. According to NEC Chapter 9, Table 8, the resistance of number 8 copper conductors is approximately 1.264 ohms per 1000 feet. Secondly, calculate the voltage drop using the following formula. Voltage drop equals 2 multiplied by the length of the conductor in feet multiplied by the current in amps multiplied by the resistance per foot. The length of the conductor is 300 feet, the current is 40 amps, and the resistance per foot is 1.264 ohms divided by 1000, which equals 0.1264 ohms per foot. Therefore, the voltage drop equals 2 multiplied by 300 feet multiplied by 40 amps multiplied by 0.1264 ohms per foot, which equals 30.34 volts. Thirdly, calculate the percentage voltage drop. Percentage voltage drop equals voltage drop divided by the source voltage multiplied by 100. The source voltage is 240 volts. Therefore, the percentage voltage drop equals 30.34 volts divided by 240 volts multiplied by 100, which equals 12.64%. Since the percentage voltage drop exceeds the recommended limit of 3% for branch circuits, the number 8 conductors are not adequately sized and must be upgraded to a larger size. By understanding these concepts and applying the relevant NEC tables and calculations, electrical professionals can ensure that conductors are properly sized and installed to provide safe and reliable electrical power. In conclusion, properly sizing conductors for a transformer installation involves several key steps and considerations outlined in the NEC. Firstly, accurately determine the transformer's primary and secondary current ratings based on the nameplate information. Secondly, calculate the minimum ampacity requirements for both primary and secondary conductors, ensuring compliance with NEC guidelines, specifically 125% of the primary current rating and 100% of the secondary current rating. Thirdly, Select appropriate conductor types and sizes based on their ampacity ratings, considering factors such as insulation type, temperature rating, and installation environment, consulting NEC Table 310.16 for guidance. Fourthly, account for any applicable temperature correction factors or conductor adhering factors, especially when conductors are installed in high ambient temperatures or in raceways with multiple conductors, utilizing NEC Tables 310.15. V2. IN 310.15. V3. I. Fifthly, ensure that equipment grounding conductors are properly sized in accordance with NEC Table 250.122, providing adequate grounding protection for the transformer and connected equipment. Sixthly, verify that all conductor terminations and splices are made using approved methods and connectors, ensuring secure and reliable connections. Seventhly, consider voltage drop, especially for long circuit runs, and select conductor sizes that minimize voltage drop to acceptable levels, as recommended by the NEC. Eighthly, provide appropriate overcurrent protection for the conductors, selecting circuit breakers or fuses that are sized to protect the conductors against overload and short circuit conditions in compliance with NEC requirements. By following these steps and adhering to the NEC guidelines, electrical professionals can ensure that transformer installations are safe, reliable, and compliant with applicable codes and standards. Always consult the latest edition of the NEC and local electrical codes for the most accurate and up-to-date information.